sign value. So the heat change sign value. Negative is exothermic or exergonic. Same thing. If it's positive, it is endothermic or endogonic. Or, sorry, endergonic. Exergonic or endergonic. They mean the same thing as exothermic and endothermic. So, finish up with sign values there. One thing to keep in mind is all physical and chemical changes will have heat loss or gain. All of them. Sometimes it's very, very small. Sometimes it's very, very large. And again, heat loss or gain is the enthalpy change, the delta H. Well, somebody help me out here. We have iodine solid going to iodine gas. This is a physical change. This is, of course, sublimation. Mrs. Ellick takes solid iodine in a sealed flask, gently heats it, and it turns, the solid goes to a purple gas. And it skips over the liquid phase and goes from solid directly to gas. Dry ice. Solid carbon dioxide goes directly to gas at room temperature. Somebody help me here. What's the sign value?
Positive.
Positive. What about this next one? We have solid magnesium chloride. We're adding water, so we're dissolving it in water. Notice we have aqueous magnesium ions. We have aqueous chloride ions. This is a strong electrolyte. Let's see here. These ions are becoming hydrated. What is the delta H of hydration for all hydration processes? Somebody at home.
Negative.
Delta H negative. Let's see what we have here. Lithium nitrate solid. Notice we're going from solid to a gas here. It obviously, these are very much attracted to each other. The nitrate's negative. The lithium is positive. You have a solid ionic compound, crystalline solid. It's going to be have a very high melting point, which tells you it takes a lot of energy to separate those negative and positives from each other. Well, again, if we go here from solid to a gas, what's the name if we want to convert a mole of ionic solid into gaseous ion? Somebody, you guys at home, anybody? A mole of ionic solid into gaseous ions, anybody? Cam Fan.
Wait, what was the question?
What's the when we convert a mole of ionic solid into gaseous ions, that definition applies to what type of energy?
Like positive or negative?
Well, I'm looking for, I gave you the definition. I'm asking for the vocabulary term that's associated with the definition, and then we can do negative and positive.
Sublimation.
Well, this is a sublimation-like process, but sublimation would be for a I guess actually I think we'll accept that. But what I was really looking for was lattice energy. Lattice energy is the energy required to convert a mole of ionic solid into gaseous ions here. That's symbolized U, so let's write lattice energy. And obviously, just like CAM-FAN, just like if it was sublimation, we would have a positive value on the lattice energy. All lattice energies are positive because it always requires energy input to separate those ions from each other. They're highly attracted to each other in the solid form, so you got to get in there, a lot of energy to separate those and create a gas from there. So that is positive. What about this one right here? Somebody else, Isabel Drosty, chlorine gas goes to 2 chlorine gas atoms. What is the enthalpy sign value for this process?
Positive.
It's positive. Let me just show you this. Let's say we have, we'll go back to, I'm assuming you got to Lewis structures last year before COVID. But if we were looking at the Lewis structure, which shows the lone pairs of electrons, we'd have something like this. Notice this is 2 chlorines. There's the single covalent bond. That's a shared pair of electrons. We could write it this way if we choose to, or we can write it with the line there. So that's chlorine gas with the lone pairs of electrons. That's a nonpolar gas. Just as a reminder, nonpolar gases tend to behave more ideally. They tend to compared to polar gases when conditions of pressure and temperature are the same. So we're going to have to add energy to break that covalent bond. And then notice what we'd have. We'd have Cl, and we'd have, there's our lone pairs. Now we've separated this, so now we've got 2 Cl atoms. And enthalpy change here, when we're going to break that bond, the enthalpy change is going to be endothermic. It's going to be positive. We could look that value up, and then the beauty of looking that up is we'll get a value for the bond enthalpy, it's called, and then if we put a negative value on that, then we know this process. We know that energy is released when these 2 come together to make that. So the forward reaction is positive, and the reverse reaction is negative. Take a look here, gas going to a liquid, that's condensation. Let's say enthalpy change here is going to be, what is it? Somebody who hadn't spoken up, Owen? Going from a gas, H2O gas to liquid, it's condensing into a liquid. What's the sign value?
Negative.
Negative, and it's approximately 40.8 approximately kJs per mole, negative value. What about this? Let's go from a solid to a liquid. So this is H2O solid. Let's go here, enthalpy change for this. We are melting this, and that's the enthalpy of fusion. And obviously, when you're melting ice, the ice is taking in energy from the surroundings into the system. And this would be positive 6.01 kJs per mole. Question? Let's talk about a dissolving an ionic solid into water. So go ahead and write enthalpy of solution. So everybody, let's start with an ionic solid here at a certain energy level. Let's put negative and positive. There's our ionic solid. Well, when we put that into water, we stir it up. We can break down that process, and it is complicated, but we can break it down into two relatively simple steps. The first step is the lattice energy. That's the energy required to separate that ionic solid into quote-unquote gaseous ions. So we're going to add energy. So notice it's uphill, and we're going to separate these ions from each other. That is U. So there's the lattice energy. Notice that is positive. Well, remember, we put this into water. We've added energy to separate those ions from each other. The water will spontaneously, because of the polar nature of water, get in and hydrate those ions. Let's say that the water comes in and hydrates these and puts us way here. So this is the delta H of hydration. This delta H of hydration is always negative. This is always positive, as we said. So let's just emphasize that. Always positive, always negative. What's the overall enthalpy change of the solution? So the overall, this is for the solution, it's going to equal U plus delta H of hydration. Down here, we have hydrated ions. I'm going to draw just a couple of them. You would have to do this too. Make sure you can see that. You would have to show the proper orientation. Here's one of my ions that's hydrated with water. Here's the other one. So let's see here. Actually, let's reverse the orientation here. Water, the oxygen is going to be pointed. Oxygen is partially negative, so it's pointed at the positive. And now we've got this with these waters hydrating with a different orientation. Look at the overall change is U plus this. Now, that's the negative ion here. Let's not, and this is the positively charged ion here. Gas, quote unquote, gas, quote unquote. It looks to me like U and the delta H of hydration, it looks like this. This is more negative than this is positive. So the overall change is going to be a negative enthalpy change. So we add this value, we add to that highly negative value here, and here's the overall enthalpy change if you add those two up. Would this ionic solid, would it heat up the water when you dissolved it in the water? Of course it would. It's exothermic. It's releasing heat. The chemicals are releasing heat into the water. The water's increasing. We have a hot pack. And what do you know? Voila. Here's another type of hot pack. This does not involve a water solution. It involves the system here. This is powdered, very fine, high surface area, powdered iron on the inside of this bag here. We're going to open that up. We're going to activate it by squeezing it. That's going to allow some air to get in. So now the air, which has oxygen, is going to react with the iron powder exothermically, and the system here is going to be the iron and the oxygen gas. The surroundings are my hand, and this is going to heat up. And the beauty of this particular hot pack is this heat up easily 4 to 5 hours. It says 10 hours of heat. I'm a little skeptical about that, especially in a practical situation. If you're out in very cold temperatures and using it, I'm sure if we just activated this indoors, it would stay hot for 10 hours. But anyway, there's the idea. Knew that'd come in handy.
Mr. Walters?
He left. Yes, what?
Are you gonna post the recording on Google Classroom later?
I'm planning on it.
Okay, because I have to go.
Oh, this has been so enlightening, though.
It has.
Okay. What we're going to do now is do a simple Hess's law. We're going to do a simple enthalpy and figuring out the enthalpy of a reaction, which is no big deal. You're just looking up the enthalpies of formation, and you're taking the products minus the reactants, and don't forget we times by stoichiometric coefficients for the balanced equation. Let's just let's take a look here. You guys need open up your books just so you have the enthalpy of formation numbers in that table. And take a look at the enthalpy of formation equation where you can figure out the enthalpy of the reaction. Take a look. We just did it last class period. So look at the formula. One of the last formulas that you have in your notes. Maybe the last. What is the enthalpy of formation of elements or molecules in their most stable state? So their most stable state, Preston, what's the enthalpy of formation?
0.
Yeah. If you have iron solid, that's 0. If you have magnesium solid, that's 0. What if you have oxygen gas versus ozone? One is O2, one is O3. The most stable form of that allotrope, and that's what it's called, an allotrope. The most stable form is we're gonna give that an enthalpy of formation of 0, and we will measure other enthalpies using those zero numbers as, get this people, sea level reference points. So those zero values are sea level reference points by which we can compare the other chemicals in a chemical reaction with the heat change. Okay, I chose just a couple simple, fairly simple examples, one with Hess's law and one with determining the enthalpy of formation. Or the enthalpy, use the enthalpy of formation to determine the enthalpy of a reaction. Let me bring that up. So be patient here just for a moment. All right. Notice, so I'm assuming, I didn't check that answer, it's in my handwriting, so I'm assuming that's the right answer. But anyway, I just scribbled that in, who knows, maybe 2-3 years ago. But anyway, here's the reaction. Notice it is balanced. So you need to look up the enthalpies of formation of this and of this, times by 1, times by 1. Then that's your products. Then you're going to subtract it by the enthalpy of formation of the reactant here, times it by 1. And should be easy enough. We'll see if that's the correct answer or not. So this is your job. And we'll check. Sign value is important. You should be real close to getting an answer at this point. And again, products, enthalpies of formation, times it by 1, add it to the enthalpy of formation of this by 1, add those two together, then subtract from reactants. Only one reactant. I'm curious, what kind of numbers have you gotten? What do you think? Anybody? Boy, this is an important reaction, by the way, calcium carbonate. So while you're doing that, the bluffs are essentially calcium carbonate. This is limestone, and the limestone is quarried. And the limestone is going to be used to make calcium oxide, which is called quicklime. And we'll just let this float off into the atmosphere and contribute to global warming. Of course, cars are dwarfing the amount of CO2 production compared to this industrial process. Got all sorts of uses of quicklime, and if you recall, one of the uses is in the mining of magnesium from the sea. Okay, so I've talked plenty. We should have an answer. What do we got, Preston?
Is it 581.3 kJs per mole?
I do not know. I haven't done it. I'm trusting you. Do we have confirmation on that? Isabel, what'd you get?
I got 460.8.
So we should not be this far off, people. What'd you get, Isabel?
I got 964.
We should not be this far off. What is this value? Say it to me. What is it? Tell me.
The CO2?
Yes. What is the enthalpy of formation?
Oh, I see what I did wrong. I misread it.
What do you got, Isabel? What do you have for CO2?
CO2 is negative 393.5.
Okay, and then we're going to add that to we'll add that to calcium oxide. What do we have for calcium oxide? Isabel.
It's negative 635.6.
Now we're going to add those two, and what do you get?
$1,029.1, and that's a negative.
Got to have that negative, and then we're going to subtract that from what number? What is this value with the sign value?
Negative 1,206.9.
Now, people, remember in freshman algebra, we've got a negative value. We're subtracting from a negative number, which makes it positive. Is that where people went wrong? We have a negative value, and we're subtracting from another negative value, which means we're going to add it. And what value do we get when we add that number to that highly negative addition of calcium oxide plus carbon dioxide? What do we have now?
I got 177.7.
Ah, there's the number in front. Isabel S. What'd you get?
I got 177.8.
Did you get that originally?
No, I had messed up.
I'm just curious. Where'd you mess up here? What?
I just wrote down the wrong number.
Oh, okay. So you gotta be meticulous. Isabel Drosty, where did you have a problem? I just need to know so I can just kind of understand for maybe the next person that comes down the line. Where did you come up wrong?
I just had my sign values wrong, so I added instead of subtracted.
Okay. Do you see it now, though? So that's what's important. Owen, how'd you do?
Good.
Okay. Owen, no big deal?
Nope.
Okay. Let's do a Hess's law. These are allotropes of sulfur. Sorry you can't see that, but that's sulfur. These are the names of the allotropes, like diamond and graphite are allotropes of carbon. So we want the enthalpy change for the bottom process using the top. There, I think you can see it all there. Remember, in Hess's law, we're going to rearrange the given reactions to the reaction of interest. And when we rearrange, if we reverse this, the enthalpy change sign value changes. If we keep it the same, obviously the sign value remains the same. I might have to times everything by 2 in order for it to cancel out with the bottom. Looks like in this case you don't have to do that. We're using Hess's law here to determine the enthalpy for this process, which maybe would not be practical to do in a lab. So it's not practical for any number of reasons to do in a lab, but still we can use these, which can be done in a lab and are accurate, to determine this process, which is kind of powerful, really. Who's got an answer? Who at home? What is it for this process? What'd you get? Owen, what'd you get?
I'm almost done. 1 second. Is it negative 0.03 kJ mole?
We want to keep this, let's just do this together. Just out of curiosity, Isabel D, what'd you get?
I got the same thing.
Let's see, what'd you get, Preston?
I also got the same.
Okay, so we'll keep this as is, and we'll keep that negative value. Let's flip this around. Let's flip the reaction around. What's going to cancel when we flip this reaction around, making monoclinic on the right side, and oxygen gas is going to be on the right side, and SO2's on the left? Won't SO2s cancel because they're on the left and right of the arrows? Yes or no at home? Won't the oxygen gases cancel?
Yeah.
What happens to this sign value? If we flip-flop this reaction, if we flip-flop it, what happens to the sign value?
It goes to positive.
It changes. So let's simply add 296.06. Let's put a negative on that. And then we're going to add it to 296.36. And go ahead and replug that in and see what you get. And what'd you get, Preston?
Is it 0.3?
What'd you get, Isabel?
I got 0.32.
And what'd you get, Owen?
0.3.
Yeah, so I don't know. I had 0.3 also. That's why I was re-going through it. We okay with this process now?
Yep.
Now it's your turn. What I'm assuming you maybe would want to do a strong acid, strong base enthalpy that would be maybe similar to what I sent out for practice for the test, which is actually homework. Yes or no? What, like from what I sent out, we did like a work, gas expansion, etc. I'm assuming that's straightforward. We've done examples in class like that. Correct? Give me something on the practice questions that I sent out, something besides the strong acid, strong base, just so I know. So the strong acid, strong base, that problem that's the one you actually came for, maybe? Let me do this. All right, let's do it. Does anybody have that sheet in front of them? They could just read that series of questions off. Anybody?
I'm pulling it up right now.
Okay. I'm not going to do that exact question. I'm going to do one like it because I still want you to do that and use it for practice. Actually, I think I remember practically everything on there, but I don't have it right in front of me either.
Mine's not loading.
Okay. Let's do this. This will cover just about everything that's on there. Again, it's different numbers, all right? Let's go 200 mils of base. We're going to call it XOH. And we're at 0.20 big M plus 100 mils of X. Let's go HX aqueous. And that is 0.15 big M. So this would be our strong base. Here's our strong acid. You guys like the little pictures or not? Like a little, okay. So here we are. This is our solution. And there we have 200 mils. Here's 100 mils. And this is XOH, aqueous. It's positive. That's H positive plus X minus. What if I ask for the pH of both solutions? Even though we're dealing with XOH, I know this is a strong base, so that's so I know these are ionized 100%. Here's a strong acid, so H positive, X minus, X could be Cl minus, I minus. Take your pick of a halogen. This could be any of the alkali metals, Na positive, K positive. Could be cesium positive, Cs. But what if we want to know the pH of this? Well, all we need to know for the pH, this is the concentration of hydroxide. So we got POH is going to be, POH is let's just go with 0.689. So the pH equals 13.3. I could adjust for sig figs, but that's not the point here. Somebody give me the pH, somebody at home. What's the pH of this strong acid solution? All I need to know is that. What do we have? Help me out, please. I like activeness when you're listening to a lecture, so you're following and participating. What is the pH of my strong acid? Help me. Isabel Drosty, what is it?
I actually don't know how to find it.
Boy, I'm glad you're here. I am so glad you're here. Preston, what is it? Isabel, what is it?
I also do not know.
I'm glad you're here. Owen, what is it? I can't hear you.
It's just negative log times 1.0.
Yeah, here's the formula. pH equals negative log of the hydrogen ion concentration. POH equals negative log of the hydroxide ion concentration. Notice for this, there's my hydroxide concentration. I simply plugged it into this, got the POH and the pH. Now, Isabel Drosty, now plug it in and give me an answer. I think we worked on this individually like 10 different times, and you got it right like 10 times in a row. So what is the pH? You're muted.
0.82.
That's it. Boy, that was so difficult. So here's the pH. Notice I'm simply plugging in the moles per liter. The brackets mean big M, so that's moles per liter. So we plug this value in, and yes, the pH is 0.824, or we could round it to 2 sig figs. Star that. We shouldn't, you're going to see that tomorrow on the test, but it's going to get much more difficult than that. Next, go ahead and write let's combine the two solutions. Write the net ionic for this strong acid, strong base. So write the net ionic. So we're going to add this to this. Notice 300.0 mils total. Strong acid, strong base. Any strong acid, strong base has the same net ionic. It's hydroxides. I'll actually put H positive first. So hydrogen ions plus hydroxide ions yield H2O. Let's put aqueous, aqueous. There's the net ionic. What are the spectator ions? The spectator ions are going to be X positive and X minus. So again, those spectator ions could be sodium ions, could be Cl minus ions, so just the negative and positive. Might be better, just to avoid confusion, to have this as HY. So we have X positive plus Y negative. These are spectators. Next, we've combined the two. We measure the temperature. The original temperature was 20.0 of both solutions. So go ahead and write original temperature, 20.0. The final temperature of the combined solutions. Let's just keep the change in temperature real simple to do. So the final temperature is 24.0.
What was key initial again?
20.0. Now, what I want you to do is, let's assume that the density of this solution is the same as pure water. And go ahead and write the specific heat of water, S. Put that off to the side. So here's specific heat of water, S equals 4.184 joules per gram times degree C. Density of the solution is 1.00 grams per mil. What I want you to do, figure out the Q for the solution, the Q value with the proper sign value. I'll put up the temperature here, 20.0 degrees C, that's T1. T2, 24.0 degrees C. Give it a shot. This is a coffee cup calorimeter. And notice, whatever is lost by the solution, negative for the solution, has to be gained by the water. The chemicals are going to be the system. The water is going to be the solution. Oh, sorry, that didn't come out right. The chemicals are the system, which are the solution. So here's the chemicals are the solution, which are the system. I boxed the system here. That is the Q for the solution. Now the water's everything else. So there's heat flow. So notice the water's gaining heat. So that's the water. All right, easy figuring out the heat gained by the water. Very easy, because we know 300 mils equals 300 grams because of this relationship. We know the specific heat here, joules per gram per degree C. Well, let's show canceling, be systematic. My answer comes out in joules. And notice my change in temperature, change is final minus initial, so 24.0 minus 20.0. That's a positive value. This is all positive. That's the gain by the water. But we know that whatever was gained by the water was lost. So the Q for the solution here, Q for the solution is the same number, but now we have a minus associated with it. We've got this as one part of our answer, but now we also know that whatever was gained had to be lost, so now we need to realize there's the Q for the solution. So far, is it making some sense? Yes,
Mr.
or
Rupert,
yeah, go ahead. Ask questions now. That's why we are here.